morning, students. Today we are going to discuss about the solution of Fredholm integral equation by successive approximation method. The solution of Fredholm integral equation of second kind by successive approximation method. It is also known as the Newman's series method. The solution of the Fredholm integral equation of second kind by successive approximation method. It is also known as the Newman series method. Rather, it is an iterative method. It is also known as the iterative method. So we have to find the solution of Fredholm integral equation of second kind with the help of the Newman series method. We have to find first, we will find the Newman series method, and some other methods are also deduced from this method. So we have to solve here the general Fredholm integral equation of second kind. So the given Fredholm integral equation is Fredholm integral equation. Let this Fredholm integral equation is gx is equals to fx plus lambda integral a to b kxt gt dt number 1. Fx is equals to integral a to b, gx is equals to fx plus lambda integral a to b kxt gt dt. Here the function kxt is known as the kernel defined for x and t. X lies between a to b and t also lies between a and b. The function fx is not equals to 0, and the parameter lambda, this also will not be equals to 0. So this is the given integral equation known as the Fredholm integral equation of second kind. Now the process for the successive approximation. First we assume the initial approximation or the initial solution of this problem. Let G0x is equals to fx is the initial approximation of gx. Initially let G0x, which is equals to fx, is the initial approximation of the function given function gx, that is the unknown function. So the initial solution of this problem is G0x, and G0x is equals to fx. We have assumed that this is the initial approximation. Now the process starts from here. Now if we put the zero approximation, this is known as the zero approximation, initial approximation. Now if we put G0x as the initial approximation in equation number first, then we get the first approximation. If we put G0x as the zero approximation or the initial approximation in equation number first, then we get the first approximation as g1x. So g1x is equals to fx plus lambda integral a to b kxt g0t dt. This is known as the first approximation. Now when we find the first approximation as g1x, then if we put g1x in equation number first, then we get the second approximation. So we get the second approximation g2x. g2x is equals to fx plus lambda integral a to b kxt g1t dt, which is known as the second approximation of gx. So proceeding in the same way, if we put the nth approximation gnx in equation first, then we get the n plus 1 approximation gn plus 1x, which is known as the n plus 1 approximation of the given integral equation. So here we get g0x is equals to fx, which is equation number 2. If you put this approximation in equation first, then we get the first approximation. So putting g0x is equals to fx in 1, we get the first approximation of gx h. g1x is equals to fx plus lambda integral a to b kxt g0t. Now as g0t we have taken as ft. So the first approximation g1x is equals to fx plus lambda integral a to b kxt ft dt number 3. This is the first approximation. Now if we put the first approximation g1x in equation number first, then we get the second approximation as g2x is equals to fx plus lambda integral a to b kxt g1t dt. Similarly, proceeding in the same way, we get the n plus 1th approximation if we put nth approximation in equation number first. So proceeding in same way, we get the n plus 1th approximation h. gn plus 1 x is equals to fx plus lambda integral a to b kxt gnt dt. This is equation number 4. Now here also we know that the iterated kernel also used here. So the iterated kernels are given where the iterated kernels are, as we know that k1xt is equals to kxt and knxt is equals to integral a to b kxz kn minus 1 zt dz number 5. These are the iterated kernels. Now we put n is equals to 1. If n is equals to 1 in 4, then we get g2x. g2x is equals to fx plus lambda integral a to b kxt g1t dt. g2x is equals to fx plus lambda integral a to b kxt g1t dt, or this can be written as fx plus lambda integral a to b kxz g1z dz. Now putting the value of g1z, putting the value of g1z from equation 3, we get g2x is equals to, we get g2x is equals to fx plus lambda integral a to b kxz into g1z. Here g1z is equals to fz plus lambda integral a to b kzt ft dt. fz kxz g1z into dz, or this can be written as fx plus lambda integral a to b kxz fz dz plus lambda square integral a to b kxz integral a to b kzt ft dt dz, or this can be written as fx plus lambda integral a to b, this can be written as kxt ft dt, replacing z by t, plus lambda square. Here we see that in this equation first we integrate with respect to t and then with respect to z. If we change the order of integration, now if we integrate first with respect to z then t, then we get it is as lambda square integral a to b ft integral a to b kxz kzt dz, and then we integrate with respect to t. So we get it as fx plus lambda integral a to b kxt ft dt plus lambda square integral a to b ft. Now what is this? As we see by the iterated kernel, if we see that this is integral a to b kxz kz dtz, as we know the first iterated kernel k1xt is equals to kxt, so this can be written as integral a to b kxz k1zt dz dt. So by the iterated kernel this is equals to fx plus lambda integral a to b kxt ft dt plus lambda square integral a to b ft, and what is this? This is the second iterated kernel, so this is equals to k2 xt dt. So this can be written as fx plus lambda integral a to b k1xt, as k1xt is kxt, so this can be written as k1xt ft dt plus lambda square integral a to b k2xt Here we change the order of integration, changing the order of integration, and here we use the iterated kernel by iterated kernel. So this is g2x. So g2x is equals to fx plus lambda integral a to b k1xt ft dt plus lambda square integral a to b k2xt ft dt, and this can be written as gx is equals to fx plus summation m is equals to 1 to 2 lambda raised to n km xt ft dt. Gx is equals g2x is equals to fx plus summation m is equals to 1 to 2 lambda raised to m, this is integral, lambda raised to m integral a to b km xt ft dt. This is equation number 6. Now proceeding in the same way, as we find the second approximation, g2x is equals to fx plus lambda is equal summation m is equals to 1 to 2 lambda raised to m integral a to b km xt ft dt. If we proceed in the same way, we get it as proceeding in the same way, we find the nth approximation h gnx is equals to fx, gnx is equals to fx plus summation m is equals to 1 to n lambda raised to m integral a to b km xt ft dt. Gnx is equals to fx plus summation m is equals to 1 to n lambda raised to n integral a to b km xt ft dt. This is the nth approximation of the function gx, which is the solution of the given integral equation. Now if we take n tends to infinite, we get the famous Newman's series. H gx is equals to limit n tends to infinite gnx, and this is equals to fx plus summation m is equals to 1 to infinite lambda raised to n integral a to b km xt ft dt. This is number 8. So the Newman series is gx is equals to limit n tends to infinite gnx is equals to fx plus summation m is equals to 1 to infinite lambda raised to m integral a to b km xt ft dt, which is the required Newman's series. As we know that gx, which is the unknown function, and gx is the solution of the given integral equation. So gx is equals to this one is also the solution of the given integral equation. Now another method can be deduced from here. The solution of this problem in terms of resolvent kernel. The solution in terms of resolvent kernel R x t lambda. The solution of this problem in terms of resolvent kernel. We will find this with the help of this equation number 8. Now if you put it, this equation 8 can be written as gx is equals to, this can be written as fx plus lambda summation n is equals to 1 to infinite lambda raised to m minus 1 integral a to b kmxt ft dt. Now if we change the order of summation and integration, changing the order of summation and integration, then we get gx is equals to fx plus lambda integral a to b, integral a to b summation n is equals to 1 to infinite lambda raised to m minus 1 kmxt ft dt number 9. Gx is equals to fx plus lambda integral a to b summation n is equals to 1 to infinite lambda raised to m minus 1 kmxt ft dt. Now if we compare this one, if we compare 9 by gx is equals to fx plus lambda integral a to b rxt lambda ft dt, then rxt lambda is equals to summation m is equals to 1 to infinite, m is equals to 1 to infinite lambda raised to m minus 1 kmxt, which is the resolvent kernel. So the resolvent kernel can be obtained by the equation number 11. So rxt lambda is equals to summation n is equals to 1 to infinite lambda raised to m minus 1 kmxt is the resolvent kernel. Now obviously the equation number 10 is the solution of the given integral equation by the resolvent kernel method. Obviously 10 is the solution of Fredholm integral equation by resolvent kernel method. So in this manner we can find the solution of the general Fredholm integral equation of second kind by two methods. First by the Newman series and the second by the resolvent kernel method. So by the second method is the important method in which we have to first find the resolvent kernel by the equation number 11 and then we get the solution of the integral equation by the resolvent kernel method by the equation number 10. So in this manner we can find the Newman series and the method of the solution of the problem by Newman series and the resolvent kernel and the solution of the problem by the resolvent kernel method. Thank you very much.